Sorry guys, it's very hot here, so hope you guys will not leave in the middle of a talk. I mean, I would leave because it's very hot, but you should try to stay here. So, so this is a joint work with myself and a few colleagues from Tremec Research. We look into the security of radio protocols used in industrial environments. For example, when you have big machineries in the industry and you have to control them remotely. They don't use normal Wi-Fi as we're using here. They use specific radio protocols. So we look at the security of these radio protocols and what could go potentially wrong. So this is what the talk is about. So industrial remote controllers, that's the name, are devices that you can use to control basically anything. They've been around for something like 25 years. So from first models, you see down here, back in the 90s, very like basic, if you want, to more like modern controllers, more fashion with joystick, buttons, so on, no? This is one of the controllers. I took a photo when we were actually doing some investigations on the early phase of the research. So we visit different construction sites. This is a photo I took from an operator. He was basically working on a crane installation. So as you can see, there are two joysticks to maneuver the machine. There is this button here is an emergency stop button that the operator can press if something goes wrong. And then there is this. So this is the receiver that receives a command from the transmitter. It's very easy. Transmitter send a command via radio, receiver, receive a command, and then the receiver is normally connected. There are different relays, one per, if you want movement. For example, if you want to lift a load, you have one relay connecting to that engine that lifts the load. And you can connect, as I said, to anything. As I said, it's used basically in factories to move, for example, hose crane, like this one. They can use to move around like dots or anything, any load inside a factory. They're used in the building sector, so construction sector. For example, it's a concrete pump, so it's used to move around concrete. They're used in the logistics sectors for transportation, for example, in harbors, as well as in airports and so on and so forth. Overall, they're used basically everywhere, like in mining, in the mining industry, in the industrial sector in general. So that made them very interesting, right? So what we did was to start directly doing kind of war driving, if you want. So like putting everything basically in a car. So we had this box here with a laptop and software-defined radio. That's the device you use to do this type of assessments. We start driving around. I live here near Milan, in the north of Italy. So put everything in the car, go around and see what's happening, right? So we visit different sites, like factories. We went inside, we asked for permission and so on. And overall, in the first phase, we came across like something like 7 different vendors, some from Italy, of course, because we did the assessment in Italy, a bunch of others from Taiwan. Taiwan has a lot of manufacturers in this space, one from Japan and one from Germany. And you can see also on the map, these are the countries that they officially resell to. So they cover all the states, Europe, China, and East. So it's basically these vendors we came across, they're very representative of what's out there. So for this research, we used software-defined radios. So I'm not sure if you guys know what this technology is about. I don't want to go much into detail because they've been around since 10 years now. But there is a lot of actually talk on this domain. So if you have questions, just let me know after. I can give you some links on description of what these software-defined radios are. But to make it very short, they are basically devices that can be very small, like a USB stick, or bigger, like this one you see on screen. It's maybe 20 centimeter per 20, devices that you connect to your computer, and they basically allow you to implement a radio in software. So what does it mean? It means you want to, for example, implement a radio to receive the information, to receive, for example, a radio stream like FM. You can implement the radio in software, and you have this device with basically nothing, acquire the radio signals, communicate the radio signal to the computer, and then the computer does the demodulation, decoding everything, and allow you to listen to the music. You can, of course, implement any kind of radio. So you can implement a radio, for example, for tracking easily flights. So, for example, aircraft use system for communicating where the flights are. For example, there are applications that allow you to see where the flights are. No? This kind of application collect data that are transmitted by the airplane via radio. So you can implement a radio for that using software-defined radios. So these are two models. One is from Texas Instruments. It's called Ethos, and the second one is a Blade RF. It's a board developed in US by some security guys. So what we did, in our preliminary on-site testing, we developed two small radios. One is to record signals on the frequency we're supposing this device would operate, which is 433 megahertz. The second one is to reply the traffic we just captured. It's very easy, right? So this is basically act as a recording functionality, like a microphone if you want. So you have the data source, which is your radio, you put it on a file, and you also visualize on screen, and this is the opposite. It's like a speaker, right? So you take what you record, you outstream it out there, and you also visualize it. Okay, it's very, very easy. So can you imagine, guys, what happened? I'm going to play you a video if a Wi-Fi supports us here. Let's see. Do you have any audio, guys? I don't know. Oop. Sorry. How does it work here? All right, so let me stop. So basically here we have a colleague of mine in the car. He's running the flow chart to reply a signal we previously recorded. And I'm outside of the car talking with the operator that gave us the recording. So I'm there with a joystick in my hands. I'm not using it, talking with the operator while he's smoking a cigarette. He's explaining me how the things works, and you can see the crane moves. So that's first test we made, the computer being able to move a crane without touching the joystick. Same here, we have a computer connected to the RF, another software-defined radio. On the bottom of the screen, you have a original joystick, and we can move the crane here without actually using the official joystick. So this, it was clear from the beginning that we could do what is called a record and reply attack. It's a very simple attack. We are going to describe it in the rest of the presentation. And we start from here, and then we dig deeper into understanding actually what's happening, no? I hate this stuff. I don't know why people like embedding presentation in you can. Yeah, all right. So the things is this. You have a transmitter and you have a receiver. All right. So what happens is that on the transmitter you execute a command like move a crane to the right. Okay, in this case it's up. So move a crane upwards. So what the transmitter does, he encodes this command into a message, call it message 1. This message gets delivered to the receiver, and the receiver executes the command, right? So it's decode the content of a message, execute the command, very easy. If the transmitter sends the same command twice, so in a second time, the transmitter will generate another message, and this message will be sent to the receiver. The receiver will execute the command, and so on and so forth for all the different messages. So short question to you guys, to make this protocol robust, like secure against this attack we just saw, record the reply, how this message should look like? Sorry? Sequence cycling? What do you mean?
It means that the receiver cannot, will ignore a message with the same sequence ID, which has been previously received.
All right. Yeah, more or less. So what this gentleman of the first line is talking about, that this message should look different one from each other. And a way of doing it is using rolling codes. So your rolling codes is a way to encode these messages in a way that they all look different, even if they contain the same command. Of course, use a sequential ID that is incremental and uses it as a seed for a hash function to basically make these messages different. All right, this was not the case here. So we test with 7 vendors on site. All of them did not implement this very, very basic safety mechanism, right? Okay, this brings us to the first attack out of the different attacks we're going to show today. Of course, this is called the record reply. All the vendors are vulnerable. It's difficulty 1 out of 3, so it's very easy because you just record traffic and reply. So you record, for example, an operator putting down the load, all right? As an attacker, you sit close by, and then you can reply this same command when there is a person under the load, and you can basically crash the load on top of the person. So very massive, you can kill someone easily. Low difficulty, cost very low. You can do it with an SDR, like an RTL SDR. It's SDR that costs $40. With $40 equipment, you can do it. All right, so here we have another video of record the reply in our test set. So here we are recording some commands. You can see this is a toy crane that we had in our lab to whom we connect this Juco. This is a vendor from Italy. You see, we record different commands like move right, move left, upwards, downwards, and then, of course, using the software-defined radio, you can see this one is completely without battery. We take everything out. We can move the crane down. So, of course, this one is in our lab. This one is on-site to another facility. Here we run the script from the shell, where we apply a command we previously recorded. Is there any audio? I don't know. So we have 2 computers, one that generates the traffic, one that has a waterfall plot. Is a tool to see basically the signal that gets generated. So you can see basically we show that this simple attack applies to anything, like very small toy crane as well as huge like overhead crane. All right, but so of course, being security experts, we're very much interested in knowing, okay, what's more, right? I mean, one thing is reply something that you previously record, which is cool, but what about you can actually create your own packet? So you can basically create any message you want, right? So to do that, what's called actually arbitrary command execution. So our goal is to be able to create any command we want, and also target not only the one specific crane or one specific transmitter or receiver, but target anybody, anything you'd like to. So to do that, of course, you have to understand how the protocol looks like. So the transmission, right? So we said, you know, you have a transmitter receiver that communicate via radio, okay? So compared to, I'm not sure how many of you guys did reversing of radio protocols in your career, but when you want to reverse engineer something that comes via Ethernet, yes, it's a pain in the ass, but you know it comes via Ethernet. Here it comes over here. So even before doing all the over reverse engineering, you have to figure out how the signal is transmitted, not only which frequency, but which type of modulation it has, which kind of headers, which type of checksum, and so on and so forth. And it looks pretty easy on paper, but actually it's not, even considering that these vendors, they heavily use the security through obscurity as a technique, you know, to hide themselves. So there is no public documentation and nothing. So of course, this means you have to do reverse engineering. So what happened here, you have, for example, your packet. I mean, we suppose the packet was like this. So we suppose the packet had a code, which is an ID that is used to bound the transmitter and receiver together. So if I want to talk to you, we have the same code, right? So when I send a command, it will reply because, you know, it's paired with myself. So we thought there was a code, pairing ID if you want, or code. Then we thought there was a sequential ID, like something that trigger basically the receiver in saying, okay, a new message is arrived. And then, of course, the command and the checksum of the command. So if you want to move up, of course, there will be a checksum of a command up. Of course, what about if you want instead replace this command as an attacker? So instead of sending the command up, we send the command, hey, there is an emergence, right? Stop. If you want to do that, we have to figure out how the checksum is computed. And if we manage to do that, of course, it's boom. It's denial of service. Because at that point, we can over and over iterate this command, and the receiver will be blocked. So it has a lot of impact, right? Because being a criminal, you can basically, you can be sit outside of your factory at 300 meters, no problem. So you can, for example, we are in the aviation museum, you can be sit outside in the parking lot. You can generate this small command, and you can basically block the production. All right, so here we have another quick demo. This is me turning on the receiver, so the transmitter. So you will see there is a sequence to activate the transmitter, and then there will be a colleague of mine that will basically send this denial of service attack and disconnect the receiver, which is on the table. You turn it on, you see, this is on. Try again, you see, the operator turn it on again. So this is a recording we did when he tried the attack on lab. It's a lot of fun, actually. All right, so now I'll give you a couple of, let's dig a bit deeper. So let's take this use case and figure out how we did the reverse engineering, which is actually what might look more interesting to you. So first thing, when you deal with these devices in general, so when you deal with embedded things, you have, of course, to take the device apart, right? So you open the device, understand how it's made, if there is one or more microcontrollers, if there is one or more, for example, radio controllers. So in this case, there was basically this gentleman here, CC1120. This is the MCU, so a microcontroller on board. We had to decap the metal plastic on top, clean it with alcohol to find the name. Then we went to the Texas Instrument website, download the sheet, so the documentation of a MCU. Then the second step, you have to figure out the different connections. So you figure out there are 3 pins for the antennas. You have to figure out where the buses goes, and so on. And then you have 2 approaches to start with. So first is to look at the signal itself. which is okay. The second one is, we'll see later, is instead to look what is transmitted on the bus between the microcontroller and the radio chipset. So starting from looking at the signals, there are different tools. This is one of the tools, Unified Radio Hacker, URH, tool that been introduced about 4 years ago. I love it a lot, so I highly suggest you guys taking a look at these tools. It contains some demodulation schemes already. For example, here you can play around. This is one packet that has been recorded. So what you do, you record the traffic, you put it in a raw file, you load the traffic, and you can visualize the traffic. Here you can see from the traffic if you did the recording correctly and you filter out the noise, something that you have to do. You can see that there are 4 energy levels. So this looks like basically signals that use 4 different symbols to communicate. So the alphabet, if you want, is based on 4 symbols. And another interesting thing is that this part here only uses 2 symbols. And this one could give you an idea that this first part is actually the code that allows you to the receiver to understand that there is new packet that has to be processed. So to make it more robust to noise, they only use 2 signals, so that they are 2 levels, so that they are very different, no? While here use 4 to carry more data. We did a first test by demodulating in FSK. You don't see here, but there are the recordings you can see later online. The header get demodulated correctly as 6A, which that's usually the header used in this case. Yeah, but this is not enough. Okay, cool. But what's next, right? Of course, it's not easy because it's not only about demodulation. There are a lot of other things you have to figure out. For example, the bit length, the speed in which the communication is performed, and so on and so forth. So to do that, we had to go a bit deeper. So to do that, we tamper on the bus that allow the MCU to communicate to the radio chipset. So what happens? You have a controller with firmware running on the controller. When you want to generate, when you press a button, the controller generates a packet and send the packet to the radio chipset. The radio chipset is connected to the antenna. At that point, the radio chipset generates basically the radio protocol. So to do that, we use a logic analyzer. So logic analyzer, there are a lot out there. They cost around $300 usually. Allow you basically to sniff the traffic directly on the board between different chipsets. Okay, well, so you sniff the traffic, and then what? There are a lot of different protocols, low-level protocols used by microcontroller to communicate. So here again, you have to guess what is it, So in this case, they use one of the common protocol used around. It's called SPI. This is a protocol, as I said, used by microchipset to communicate. So okay, you take SPI, and then what again? And then you have to contextualize the traffic. So you see some SPI data going on, but if you don't know which kind of radio chipset is on the board, if you don't know which kind of MCU is on the board, it's very difficult to contextualize things. So our goal was to go and do something like this. So our goal was to really understand what the MCU was doing on the radio chipset. So MCU was, for example, setting the frequency on the radio chipset. So at that point, you set on the radio chipset a parameter, which is the frequency. And then you set on the radio chipset a parameter, which is the modulation. Then you set on the radio chipset the header of the packet and so on. So to be able to understand which kind of register are written and read on the radio chipset, you have to be able to contextualize the SPI protocol. So we wrote an emulator for that does this job. As a result of that, we wrote a GnuRadio block. GnuRadio is a software, as I was saying before, to implement software-defined radios in software. So we wrote this block here, 2 blocks, UCO packet encoder, UCO packet decoder. these blocks basically allow us at that point to reverse engineer all the physical layer of a radio protocol. As a result of that, we can send packets, and as much as you want, we can also receive packets. So this is a full blockchain of the receiver. We can open source that, so if you have any question or you want to take a look, I'm not going to detail all that stuff here, but as a result of all this process, we can basically we can read packets, and we can process all the physical layer, and we can also transmit. What's missing is the payload. So the payload is the data that is transmitted, how the data looks like. And so this is usually where you start when you have to reverse engineer, for example, a network protocol over TCP. Usually you start here. So you don't bother about all the physical layer, because you know that there is all the TCP/IP stack that does it. So you start from here. You start from the data. So you open your Wireshark, you see some data, in the payload of a protocol that you don't know. Could be, for example, the protocol of a command and control server, like a bot communicating with a command and control server. You saw some data. You might say, okay, is this data obfuscated? I don't know. Is this data encrypted? I don't know. They're sharing a key? I don't know. So you start from here. You don't bother about all the physical layer. While for radio protocols, if you want to get into reverse engineering radio protocols, you have to bother of all the things I've said before, like encoding, frequency, header, trailer, CRC, all the other things. Okay, so now I'm going into telling you how the payload looks like. So of course there is we thought it was like this. So preamble, sync words, trailer, application data in the middle. So what we did, using the receiver I showed you before, we basically capture all the traffic generated by one single command. So one command is, for example, move a crane up. So we press this button for 1 minute, we record, and this is what came out. So all different packets, only the payload. All right, so it looks like the payload has a sequential ID, as the gentleman here was saying. So we sort by sequential ID, and it looks like this. When we do the other experiment, so we record not only the up button, but the up button, down, left, right, so on and so forth. Then we sort by fixed sequential ID. So we said, okay, let's look at all the different commands having sequential ID too. And this is what came out. So you can see here, there is these 5 bytes for, this is an error. This one doesn't matter, it's here. These 4 bytes, they all look the same. So it doesn't matter which command you execute, like right, left, up, down. These 4 bytes giving the same sequential ID, they are all the same. So we start thinking, okay, what should be always the same into this type of communication? And then it came up this. I said, okay, you see, there is this strange 201077C8, which is printed on the board. So we thought, okay, so this could be probably the pairing ID, right? So you have multiple of this device, you want to pair a receiver and transmitter together. There is a pairing ID, no? So right, so what we did, we thought, okay, those bytes could be the pairing code. What we did, we reprogrammed both the receiver and the transmitter using a software that was shipped with the device. We set the pairing code to 0000, then we XOR the original traffic with that one after we reprogram as 000, and we figure out basically, look at this. This is the little endian form of the pairing code. Done. So after that, we figure out here, here you have a checksum. This is the checksum of a pairing code. This is not used. Here you have a command, which is encoded. And here you have a checksum of a command. So given that, done. So we figure out how the protocol looks like, both at application layer, which is this, both at physical layer. Of course, later in the talk, I'm going to tell you about responsible disclosure, how we communicate with a vendor, and so on and so forth. But this allows us to do at that point common injection, so we can inject any command. So we can do the out-of-service attack, as I was showing before. We can also repair a device. So I'm paired with this gentleman here. Me as an attacker, I can say, okay, you know what? I'm an attacker. I'm going to take full control. So it will be the original transmitter will be disconnected, and me as an attacker, I will be paired with a victim, and I will send command to the victim. Then, of course, I can also change the pairing code. So classic example, I want to steal his car. I'm an attacker. I record him pushing a button of his nice BMW. Suppose there is a vulnerability of reply attack, I can reply the command and the BMW open. But if I know how the pairing code is encoded, at that point I can steal not only his BMW, I can steal the BMW of another gentleman, another gentleman, another gentleman. Of course, changing the pairing code, I can target anyone, right? Do you see? So it goes from victimize only the gentleman from whom I record the packet to victimize everybody. Of course, it's not finished, we still have 20 minutes, so let's do it more fun. What about the firmware these guys runs? That's the next step, right? So up to now, everything was a black box. So we look at how they communicate, but we didn't look at what's actually running on the device. So to do that, we bought this device. That allows you to reprogram. So for example, when you want to change the pairing code, suppose you buy 2 of these devices and you want to change the pairing code, you can use this device. Or you want to change the frequency, you can change the frequency. So vendors gives you basically ability to change some parameters and to reprogram the devices. So we bought this controller, this adapter to reprogram the device. Then what we did, we opened the tool, the software for programming these devices, and we sniff the traffic using our logic analyzer. So it's the same guy we used before in the talk. And then we play around. We thought that they were using UART, which is basically a standard protocol for serial communication. And yes, so we are right. So we saw that there was basically a sequence at the beginning. So after when you want to reprogram these devices, there is actually a bootloader, and from the bootloader you can basically extract the password that is used to program the device. This is because the bootloader communicates the password in clear text with the software, which is very stupid, right? So you can see here, at the beginning, we are voluntarily providing a wrong password to the device, and we have a data NAC saying, yeah, the password you provide to the device is wrong. Then on the second step, we provide the right password, at that point, data hack. So we extract the password very simply using logic analyzer, because the software was communicating the password in clear text with the device. Super lame. At that point, super easy. MSP FAT. We provide a password on COM5, dump all the firmware. We dump the firmware. It's a firmware for ARM. We look at the firmware, and there is a check firmware integrity. So the device has like a CRC to make sure the firmware is correct. For example, you download the firmware, you want to update your device, you make a mistake in downloading the firmware, the device does not boot or tells you, there is a problem. The problem is that this firmware integrity check is in the firmware itself. So at that point, I can create like hijack the firmware, create, for example, a malicious firmware. I compute the CRC of a malicious firmware, and then the system auto-check itself. So it doesn't make any sense. It doesn't make any sense to have the integrity check of a firmware in the firmware itself, because you can change the firmware and the integrity functionality, which is this check info sanity. You just return true. I mean, there is no even sense. All right, so at that point, of course, a malicious actor can, this is what we did. So there was a clear text password transmission. So we sniff a password using the original software. This gentleman, for reprogramming, you have to connect it to the two devices. You can see here. And yeah, I mean, a result of that, an attacker can simply create a backdoor and put the backdoor in the firmware. So he can basically create a backdoor and say, okay, whenever the attacker sends a specific packet, whatever, you just disconnect all the load, you just make the crane swinging around, you might kill someone, you can block the production and create, for example, a ransom, like a ransomware attack, you can ransom someone, extortion, you can do sabotage, super easy. Yeah. All right. So, so after that, we said, okay, cool. But what about we develop like a software-defined radio, which instead of costing $500 or $300, it costs $40, and it's small. What about we develop this device, which is stealth? Someone can drop it inside the factory, hide it somewhere, and then we can, what about we make this device, let's say 4G compatible. So but basically to give you an idea, a colleague of mine, not myself, Federico, he developed this gentleman, it's called RFQuack. The code is made freely available on GitHub, you check it out. So this is basically tools that allow you to automate packet manipulation and packet forgery. And what makes it interesting is that with this tool, we demonstrate that an attacker can take ownership of a factory or whatever installation without being physically there. Because this gentleman has a 4G terminal, it has a SIM card, so you can basically control this gentleman remotely from your computer, so you can be sit on the other side of the globe, like here, can be sit here. I can control this gentleman that is, for example, in Taiwan, and he will act as a RF bridge. So I can send a command, say, okay, block production. This gentleman receive a command, he implements a software-defined radio, kind of. It's a hybrid software-defined radio, whatever. There is an antenna, it will generate the packet and stop the production. So this allow, in this scenario, this allow basically to take control, take ownership wherever you are. So if you are an insider, you work in a large organization and you can have these devices. First, you can drop the device on the floor, hide it somewhere. At that point, you allow someone to take ownership and control. We have a small video. If you have time, I can show you around here. So we made the tool available not to help people doing attacks, but to make the people to make the life of security researchers easier, because reverse engineering this radio protocol is not something that you do it 5 minutes. So with this tool, it makes all your life easier, because without going into detail, you can basically yeah, I mean, we can talk offline because I don't have much time, but it makes basically all the life of security researchers easier. So after that, of course, I have 5 more minutes. I want to conclude saying that responsible disclosure was a bit painful in this case, because we had to deal with vendors that are not used to deal with vulnerabilities. What does it mean? If you report a vulnerability to Facebook, they have a program for, working with vulnerabilities. Here was not the case, so it took us a long time. We work with ZDI for that. We usually 120 days of period. Here we gave way more than that. To conclude, of course, we found the different vulnerabilities. Common pattern are, not running code, as the gentleman was saying here, or wherever there was encryption was very easy, so we bypass the obfuscation with a simple XOR. If you use XOR as an obfuscation schema, not good. And also the firmware, there was no lack. There was no, the password transmitted in clear. Mass storage was not enabled. Because if you enable mass storage and you as an attacker, you wanna dump a firmware, you provide the wrong password, the firmware get erased. That functionality, which is available on our Texas Instrument chipset, was not enabled. And also the integrity was in the firmware itself. So you can, at that point, replace the firmware and change the routine for checking the integrity. For a vendor, of course, why you don't use open technologies, right? Like Bluetooth, for example. Why you go for proprietary protocols? And you don't make your protocols publicly available, so you rely on security for security. Usual things has been said for years, so we are here to repeat it again. So yeah, we released a paper. So we have a white paper with a lot of nice figures. Marketing people love that. And then we have a technical paper that we will release at DIMBA. It's an academic conference running in Gothenburg this year, end of June. So that's the link for reference. And this concludes my talk. So thanks a lot. Thanks for still being here despite the warm and almost lunchtime. So I'm open to questions if you are willing to make public questions. Otherwise, I will be in the hour round, so you can just stop by and thanks a lot.